à vous sur cette conférence sur le véhicule autonome organisée par Cara et je remercie les différents intervenants d'être avec nous aujourd'hui. Juste pour vous contextualiser, donc Cara a organisé cette conférence. Nous sommes un pôle de compétitivité. Nos missions sont principalement d'accompagner et d'apporter notre soutien pour la mutation des systèmes de transport. Et notre objectif, c'est de susciter, favoriser l'innovation, la collaboration pour développer l'activité économique sur le territoire Auvergne-Rhône-Alpes. Nous sommes une association composée de 430 membres environ et notre réseau est constitué de différents types de structures, d'organisations, donc des entreprises, des toutes petites entreprises, des plus grosses, des grands groupes, mais également des laboratoires de recherche et des institutions, des fédérations professionnelles et des collectivités territoriales. Nos actions sont principalement tournées autour de l'innovation, de l'idée jusqu'au marché. Donc en fait, on a un certain nombre d'actions qui permettent, au travers d'actions collectives, d'apporter notre soutien à nos membres. Concrètement, nos activités sont essentiellement tournées autour de la mise en réseau des différents acteurs de la mobilité sur différentes filières, de la filière mobilité active, micromobilité, jusqu'aux plus gros véhicules industriels. Notre objectif étant d'apporter notre soutien sur des projets transverses ou sectoriels. On anime un certain nombre d'événements qualifiés, experts, qu'on appelle les think tanks, qui sont tournés autour des problématiques de nos adhérents. On accompagne aussi nos adhérents sur des projets d'innovation, notamment au travers de notre soutien sur les appels à projets de financement public. On essaye aussi d'apporter notre concours sur la partie expertise et la partie compétences, qui est une partie importante sur la partie transition mobilité. On organise un certain nombre d'événements et un certain nombre de veilles pour informer nos réseaux sur les sujets qui sont importants à traiter. On a deux grands sujets principaux au sein de Cara, les questions de décarbonation de la mobilité et les questions de digitalisation de systèmes de transport intelligents. Et en fait, c'est dans ce cadre-là que Cara a contribué au projet Award, tout simplement parce que parmi nos membres, on a un certain nombre d'acteurs qui travaillent sur ces sujets de véhicules intelligents, systèmes de transport intelligents et véhicules autonomes, et notamment EasyMile qui est avec nous aujourd'hui et qui est le porteur du projet Award et qui va introduire pour le coup le sujet de la conférence d'aujourd'hui. Je laisse la parole à Benike.
Hi everyone, I'm going to switch to English. I hope that's okay. Do you have to do something on your sets? Yes, I can see you all fiddling. Hi to everybody online. I hope that's okay for you too. Okay, so my name is Benika. I'm from EasyMile, which is a technology company who is leading this project. So you guys have all come here to this session. Do you know what award stands for, this acronym? Anyone brave enough to pull off their headset and shout it out to me? I've got someone shaking their head at me. Okay, so I'll give you a clue. The first letter of that, the A, EasyMile, we're a driverless technology company. What's another word for driverless? Starts with an A. Autonomous, yes, okay. So this has a lot to do with autonomy and making vehicles autonomous. It also has a lot to do with certain environmental conditions in which these autonomous vehicles can operate. So the W in award, environmental conditions, right? Stuff that falls down from the sky. What's that W? Weather, someone's mouthing it at me, yes. Okay, so let's keep going. I'm going to go a little bit backwards and forwards. There you go, all-weather autonomous real logistics operations and demonstrations. So that is the project that we're all working on. Let me just go back and introduce you. So that's me there on the first line. You've got to listen to me for about 10 minutes. If you've got questions, feel free to wave at me, call them out. We can also save them till the end. And then you're going to hear from Olaf from Applied Autonomy, who's here all the way from Norway, to talk to us about fleet management system. Not yet, Olaf, I'm just kind of introducing you so they know who you are. And we've got Sami all the way from Finland, who's going to give you some results. Victoire from IRU, very important regulations and frameworks. She'll talk to you a bit more about that. And then we've got Diana from Cara, who I think possibly has the juiciest bit of the presentation. I'm certainly quite interested in your part, Diana. That's the real stuff, the emerging business models from this project. So let's go back. The project is part of the European Union's H2020 framework. So this is a research and innovation funding framework whereby the European Union is looking to advance certain industries and certain sectors. So the clever people at the European Union saw a gap in the application of autonomous technology on these heavy-duty vehicles in real logistics operations. So as I've said, that is the acronym AWARD. Closer? All right. EasyMile is the leader of the project. There's a lot of money behind the project, 26 million euros, and there are 29 of us in the project. It's a pretty cool mix. There's researchers, there's first and second tier automotive manufacturers, technology companies, large well-known companies to young, growing, innovative companies. So it's a really nice mix of partners. There we all are. I won't let you look through all the logos, but 29 of us. So, EasyMile's role, as I said, we're a technology provider. We built our expertise 9 years ago. We started with that little vehicle that you can see in the middle there, that passenger shuttle, little autonomous bus. We've driven more than 1 million kilometers autonomously with that bus in more than 300 locations around the world. We're the most experienced provider of level 4 operations globally. Does anyone know what that is? Level 4 of autonomous driving? Got some more blank faces in the audience. Okay, quick lesson of the levels of autonomous driving. So level 1 and 2 is what most of us are doing today. We're in smart cars, we're holding the wheel. Level 3 is when there's a very high level of technology involved and what a lot of vehicles in the award project are running under, where there is still a human on board to keep an eye on things, a bit like lifts in the old days. You'd get in the lift and there'd be someone there just to keep an eye and press the button for you, right? And then level 4, and which we are progressing to in some of the use cases in award, we'll tell you about that, is completely removing any human supervisor from on board the vehicle, and that's where it gets very cool for the technology, where the vehicle really is maneuvering completely independently. So, in this project, 4 different use cases and 4 different sets of real-life logistics conditions, 4 different vehicles that we're putting in these use cases. So the first one is on a port. So this is an autonomous terminal tractor. They sometimes call it a yard truck in different markets. The vehicle is manufactured by Terberg. I'll tell you a bit more about that in another slide. Working closely with DFDS to get this vehicle out into a live port environment, moving around these horizontal containers. The second vehicle is a big beast. This one is an autonomous swap body truck manufactured by Kamag, and this use case is in partnership with DB Schenker and Rotax. This one is quite cool because we've been able to get this one out into a public road. So that's a whole other set of complexities, dealing with regulation and framework and getting a big autonomous vehicle like this to run hub to hub from different dispatch centers on a public road. And we have been able to do that in this project in Austria. We'll tell you a bit more about that. Third one is an autonomous tow tractor. So a lot of you might have flown to Lyon. So you look out the aircraft window and you see all those little tow tractors running around the airport, towing the luggage trailers from the aircraft to the baggage handling area of the airport. That's what this is. Obviously, the objective here is to make it driverless and for it to operate in all weather or harsh weather conditions. That's why we're super pleased to be up in Norway, where there's lots of snow and harsh weather, where we're trialling this vehicle at Oslo Airport with Avinor. The last one is an autonomous forklift in Austria that we're loading and unloading autonomously. There is also, of course, I'll let you read the other column alongside that, a lot of different players in the technology here for the development of the various systems. You can see the lucky last one on that list is applied autonomy, and you're lucky to have Olav here today who's going to tell you a bit more about that, so I won't say too much more. Okay, airport. So, who remembers which vehicle is at the airport? Where is the airport? Is it here in France? Just checking you're not all sleeping yet. Oslo, right? We've got the vehicle up at Oslo Airport. A little bit about the vehicle. It's a French vehicle. We can be proud of that, being here in France, manufactured by TLD, so they're a leading ground support equipment supplier. They have their vehicles on most major airports around the world. So the vehicle is for the airport use case. Interestingly, aside from the award project, it also runs in commercial operations at big automotive manufacturers. We have one at the BMW plant in Dingolfing in Germany, one at Daimler Trucks in Germany, and quite a few in the US, and I'm not allowed to say where they are because they're all under NDAs, but they're out in commercial operation as well, which is very cool. So it's a real application for this vehicle. Fleet of 3 of them at Changi in Singapore, they're at Narita in Tokyo, in Toulouse here in France, and obviously this one in Oslo as part of this project specifically for the all-weather conditions. So how we make sure it's safe, a lot of testing goes on behind the scenes, both at EasyMiles home base in France and on the test track. I'm going to show you this video. This is great. Is it going to work? Yeah. Have a look. And of course it stops. So there's a high level of technology at play there. There's a safety chain that's been uniquely developed by EasyMile that's built into the vehicle. There are sensor sets, so it's localizing with 1 to 2 centimeter level precision at every point. So the sensors have been able to detect that obstacle in real time. The braking system obviously has worked and come into play in the rain. So the testing is obviously very, very important for these sorts of deployments. So on the tarmac, this is the real world playground, I suppose. There we are at Oslo Airport. I'll just play that one while I speak. That's on a sunnier day. We're looking forward, hopefully. Is the snow coming in Norway, Olav? Avinor assure me it is, yes. We want the snow to come. This vehicle has been through nearly 3 phases now. So phase 3 is coming up. It's had its winter tires put on last week, the week before. So we're really ready now to have some snow and put it into those conditions. And we also might try to completely remove the human supervisor from within the vehicle and run it fully driverlessly, which will be excellent. Okay, hub to hub. So this is the truck that I told you about, the one that goes on or went on public roads. So this one is manufactured by Kamag in Ulm in Germany. It can go a little bit faster than the tractor, 20 kilometers per hour. Just a note on speed. Speed is often a hot topic with autonomous vehicles. Okay, don't confuse them with driverless cars. They don't need to go any faster. This is simply shunting from point A to point B on a very safe track. It is this speed that is the safest and most efficient for the use case that it's being deployed on. Again, how we make sure it's safe, a lot of different testing. There it is on the test track. I think that's in Digitrans in Austria. The rain tunnel is a very important part of testing as well. And in this particular case, also driving forwards and backwards. There it is, going backwards. Backwards is trickier for autonomous vehicles. Yeah, you can really see the rain tunnel there. Okay, so on the road, the yellow line that you can see there is public roads. So this was between two distribution hubs in Gunskirchen in Austria. Oh, and I don't know how long this use case ran for. Any of my colleagues on the stage can remember? Don't know. It doesn't matter. It's a detail. The main thing is that it worked. We got the authorizations to go on the public roads and the vehicle was able to operate, okay? So, which is obviously the main outcome of this type of project. We've been going for nearly 2 years now, so we're very proud to be able to stand up here with you today and say we've actually done it. We've gotten it onto a public road and we've made it perform how we wanted it to. All right, second last one for the overview, the vehicle that is at the port. This is the one you first saw with the big DFDS logo on the container. So this is a vehicle that we call the Easy Tug, autonomous terminal tractor or yard truck. So it's this body here transporting these horizontal containers in a live and busy port environment, which is no mean feat. I don't know if anyone has been onto a port recently. There is a lot going on. There's a lot of deadlines. There's ships pulling in for certain times. There's truck drivers arriving who have driven right across Europe to get there at a certain time slot to deliver their goods. There's a lot going on at a port. Similar testing. Is this a video? Yes, it is. You can see it come down into the rain tunnel here in Austria. This was not that long ago, a few months ago. Obviously there without its container, simply testing. Okay, so I might just, oops. That video is not going to play. That doesn't matter. So again, 3 phases to this particular use case. Phase 1 is simply moving around on the port, that environment that I described to you before. So navigating with mixed traffic, navigating with human-driven vehicles. And I also want to take a step back and stress there. I think when people hear autonomous vehicles, oh, that's it, you're replacing all the drivers, it's all over. No, it's about integrating and adding capacity and adding efficiency and getting different types of vehicles into use and in the mix at the same time. So that was the first phase of this particular use case. Phase 2, there was a public road aspect to this one as well, a small roundabout that the vehicle had to pass through, and also gate process. This was quite cool to see as well, that as the vehicle approached the gates at the port, Applied Autonomy had a role in this. Olaf will tell you more about that, as well as DFDS, that the gates were able to recognize the vehicle and open up. Phase 3 was very cool. We actually released a press release about it just yesterday. I hope you've all seen it on LinkedIn and on the various channels. So phase 3 was autonomously, of course, loading and unloading the trailer onto a ship. So I don't know if anyone knows port jargon. This is called ro-ro in the port industry. I was quite pleased with learning that one. That means roll on, roll off. So the ship arrives at the port, the ramp comes down, and the terminal tractor autonomously is able to navigate that and roll on, unload the container, and roll off, which again is no mean feat for an autonomous vehicle. There's a lot of obstacles, there's a lot of different things in the way for it to be able to geolocate and navigate all of that, and we did that within this project at the port of Vlaardingen. Last one is the forklift. Very briefly, this is designed to be an outdoor and off-road machine. It's usually used for loading and unloading at sites without logistics infrastructure, and was able there to navigate directly up to the truck under remote control to load and unload. So 4 different vehicles in this project, 4 different use cases, driving autonomously in all weather conditions. And I think that's it from me for the overview. How are we doing for time? We're okay. 10-15 minutes for you, Olaf, to tell us a bit more about Applied Autonomy's role. Here's the clicker.
So thank you, Benedict. Thank you for having me. I will describe a use case within the port where there is, you can see the sea there. There is 2 factories. The distance between the port and the factory at the right is 3.5 kilometers. So between the port and the factory off to the right, it's 85,000 TEUs. Do you know what a TEU is? It's a 20-foot container. So, and shipping is mostly on raw material is in containers, and it's also exported in containers, and that is also a part that we have to take into account when we do the planning of logistics. And I will show you then how is the fleet management system a part of automated transport with autonomous vehicles. That is the topic. So this is the way they do it when they do it manually. They have the unload of the container into a terminal tractor, or they can do it with a terminal tractor and a special type of trailer, as you can see, that lift up the container. And then they have a straddle carrier that moves it around. Straddle carriers is very flexible. But this is the way they do it when they do it with regular vehicles. But it have a cost. The distance is 3.5 kilometers. The average speed is 14 kilometers an hour. And with this volume, it's 14 full-time drivers for the terminal tractors. In addition, it's 8 full-time drivers for the reach tracker. This means that it's 22 full-time drivers that cost 2 million euros annually. So it's quite high cost. It should be a good business case. And we have seen, then Benedict have told us about the best virtual driver, the autonomous vehicle. There is a driver, but it's virtual. It's the software and the sensor that drive. But these vehicles, they stand still if they do not get the tasks. And the tasks and the approval to go around. So there must be a human in the loop. And that is, the human in the loop is coming in by the fleet management, operational tool and automated logistics, and for 24 hours a day. So at the left you see the best autonomous vehicles, and the right side you see the fleet management and operation tool. It's in the tool, it's in the cloud, and you have connections to the vehicle, two-way communication to the vehicle driving system. It has two-way communication to all the equipment that you saw that is involved in the flow. But I will show you then how it's disconnected. So first, containers are coming to the port to be up to the import side of the factory. There is raw materials in different types and within the containers. So you can see that the equipment that is used is under the bottom. Above that is the flow. What is the activity of the flow? And above that is the fleet management system that is integrating. And at the top there is some external system that we are communicating through. And just for the flow of import, there is 7 systems that are integrated. Under load, then it's the crane system. On the transport, it's the vehicle. On the port gate, to get out of the port with these goods, there is a new gate. So there is a gate that you need to be authorized this truck to go out there with a container. Then it's transport again, then factory gate to get into the factory. The transport have to be authorized. This is all done manually today. So when we automate this transport, we need to integrate it to make it autonomous, because there cannot be a person running out every time this integration is there. Then after the port gate, it's a factory gate, it's the transport again, and then we come to the unloading gate. And here Benedict showed us also now it's possible to go backward with this Kamag vehicle. Then we can also remove the remote driving. We might have a person from the beginning looking that everything is going well, but remote driving is not necessary, and that's very good. Because remote driving is not the part of the solution, I would say. It might be just to see. So this was the import part of it. Then we go to the transport of the containers from they have been unloaded, the goods. Now they're ready to go to the export gate, the materials that is already produced. But before they can go to the export gate, need to be checked that they are clean. There I use the human, but it's the sensor there that look into the container that is clean. But it's an external system again. Then it's remote driving that is not necessary. That is transport, cleaning, transport again, remote driving, not needed, and then it's load. There is written wrong, it should be load on the last arrow there, and then it's 10 systems in total so far that is integrated to the fleet management system. Now I think you understand more what a fleet management system is. It's about integrations and flow of the production. And the last one is then the transport from the export gate down to the port. Remote driving is not needed more. Load, transport, factory gate out of the factory with these nice produced batteries. That is battery factory. Then it's transport, port gate, transport, and then outloaded to a stack of containers that is ready to be on a ship. So the last part that is manual, that is the external system number 11 at the far right, because that is a reach stacker, and the reach stacker is not part of this project, so that is manual. So 11 systems for this case have to be integrated. And is it usable and affordable? That is also a part of this project, but what we have done in this project is very much to make the vehicles prepared for drive in snow, rain, all weather conditions. And this port here, this is far more north than Gardermoen. There is much snow already. So my message here is that this solution that we have built now can be usable, but we must be testing more to improve the last part of it. So we must not stop here. More pilots have to be done, and also to build the knowledge among the users, because the users that are operating terminals today, they are used to drive. So it's a shift of their processes to be managing processes instead of driving process themselves. So that is a big shift, and to help them to understand this shift and the business cases of it, pilots is needed. And also 11 integrations, that is also a part of it. So it's not just making these vehicles driving autonomous, but it's also about the integrations. As you can see, it's very important for a terminal operator to have the ability to integrate many different equipment. So the question here is also, is it a good idea to integrate all this system directly to a vehicle? No, it's not a good idea, because there are many different vehicles out there. So any questions? Claire? Okay, good. I think I was finished before 15 minutes, Benedict.
Good afternoon, I'm Sami Koskinen from VTT Technical Research Center of Finland, and I'm going to discuss the first evaluation results of this award project. As you have now heard, we have 4 test sites, a port, airport, 2 industrial sites. I'm going to discuss the results from the first 3 that are more or less ready. Our tests are still ongoing, and the final evaluation results will be presented around next summer. So all our tests have used the FESTA evaluation methodology for setting up these field operational tests. It's a rather popular methodology. And besides the actual tests, we also do simulations to consider what would happen if more of such vehicles would be automated. So let's start from the Oslo tests, where we had this automated luggage tractor. The first tests were done in June 22. And then we had some 60 hours of operations back then, and then we wanted to examine as one thing how much human support is needed in the first phases. And then we saw it was very much affected by other human-driver interactions. So other humans, like in the bottom figure, they tended to leave these luggage carts on the route of the automated vehicle, and that was the major concern in this percentage. So we saw that the safety driver and in the future / teleoperator would have to rather frequently overtake these such luggage carts and to handle the interaction with human drivers. In the tests we saw that some 15% was needed for the safety driver to support the vehicle, but much of that was due to our test-related documentation. So our first conclusion here is that maybe 5 minutes per hour would be the need for human support. However, if the human and automated operations were to be more separate, then automation can probably run on its own for 2 weeks without anything. But it's really the interaction with human drivers. Regarding our other results, tests went fine. Operators felt safe in the vehicle, and such was the case for all of our tests. We saw that for a trip that takes 7 minutes to drive for a human driver, the automation took 10. But both timings were fine enough for the airport operations and capable to move luggages in the airplane turnaround time. So it's a compact airport, and both performance numbers are satisfactory. The automation drove 15 kilometers per hour and humans 20 to 30 kilometers. But that did lead to one safety concern, which is overtaking. And the vehicle was rather frequently overtaken, and this is something to investigate further. The vehicle could, of course, drive a little bit faster. Regarding, let's say, future integration lessons, we see there is certain need to control the other ground handling vehicles that work around the airplane. For example, a fuel vehicle can take 3 different angles near an airplane, so the automated vehicle, to know where it should stop, would have to recognize where the fuel vehicle and other actors are, or there would be a need for some fuel fleet control. Also then, the hooking and unhooking trailers, even these luggage carts, it's currently in the Oslo process. The loading and unloading these luggages from the carts is a rather separate process and requires these carts to be separate, whereas the driving is then another process. And then for automation to completely handle this, it should have to be capable to hook and unhook the trailers automated, or otherwise the processes could be considered. This is a general lesson from all the tests we see, that it's not only the driving part, it's also the other industrial processes that have to be considered. We did some simulations for each of our test cases, and then for airport we see that the number of vehicles doesn't really change. For meeting the quality requirements for delivering luggage in 15 minutes, we need either 30 automated or 30 human drivers. But we see that if we now assume that we move from human drivers to teleoperation cases, and then 5 minutes per operational hour is needed per vehicle in teleoperation, then human work time would clearly drop. And then we can then also consider that today human drivers, they have to wait. So this is the working and driving time that would drop to half. But if we consider the human waiting time, the costs and the total work time would drop even to 20%, considering this 5 minutes support per hour. But to reach such capabilities, certainly the integration topics have to be achieved. One topic of interest is that automated vehicles drive 4% less than humans. This is due to humans needing to go to breaks and lunch hours, and the difference is not huge, but there is clearly a difference. Our second case is the hub-to-hub logistics in Austria. So in this one we automated a goods transfer between 2 industrial sites. The tests went well, especially the driving at the industrial areas. The most difficult segment was the public road segment here. The speed limit is 60 kilometers per hour and the automated vehicle does 25, 29 maximum. So that gave that a certain queue was formed. However, there were not overtaking cases that much. This is a rather short segment, and it was possible. And then we also needed an extra traffic light because this vehicle enters the road segment rather carefully, and we wanted to keep it red for the others. So in average, humans drive the route in 16 kilometers per hour in average, and an automation around 6. However, that was not an issue either in this case. The driving happens only once an hour, and the loading is the big thing here. Some of the lessons further, I mean, the traffic light, first it was set so that humans had to wait more. Later on it was better in sync with the automated vehicle, but before it was in sync, humans started to ignore the traffic light in the evenings, especially after 30 seconds, and this was a safety concern in the sense. For eco-driving, we see across all our tests that it's really dependent on how much the vehicles brake, and because starting again with this heavy load takes energy. And in this case, we had a LiDAR laser scanner data filter not present there, and the vehicle became overly careful. I mean, if a leaf was falling from a tree, it stopped. And this meant that it also required some more energy than humans. But this is something that can be worked on, and the other test vehicles had a way better eco-driving performance. So we know from our experiments practically that the eco-driving aspect varies from plus minus 20%, depending how much these vehicles brake. And let's say normally it's around 0. There is no much difference. But if the automated drives very fluently, then it can save some energy as well. Regarding the stopping reasons, we had the LiDAR data acting up, but we also had this rather difficult road segment, the high-speed segment, but we are using map-based positioning and LiDAR-based positioning, and it has a lot of vegetation which grows over time, and how up-to-date is the map is a topic then, and how the vegetation is maybe low-hanging and even touching the vehicle, and for collision avoidance purposes the vehicle has to drive rather carefully. And many of these stops were due to this type of a vegetation topic. In the end, this vehicle did require some human support. Here we are talking some 10 minutes per hour, but these are not, I would say, final numbers. These are the test numbers that we are working on. The simulation case is about a couple of things. First of all, these electric trucks can sometimes choose another route than the current diesel-driven vehicles. So thanks to less emissions and less noise, they choose another route, which here in this case is 26% shorter. And again, if we consider the teleoperation need of 5 minutes per hour, human work time would clearly be reduced in this case. However, now this case is an example of where we are moving one driver to become a teleoperator, and there is no savings in that. But we could see a business case in future that if there is a third-party teleoperation company that oversees, say, 50 of similar industrial sites, then the driver can be removed, and we have a limited number of teleoperators overseeing such vehicle fleet. That is the way here, from simulation perspective, to achieve the savings. But clearly the work need is less. We move on to the third test site, which was the DFDS terminal in Rotterdam, and it's a trailer terminal, as you see. The trailer terminals are about speed when compared to container terminals. We saw the most benefit for automation in rearranging the trailers for faster ship loading. So when the ships arrive, the trailers are in perfect order close to the ship and not scattered across the yard. However, even though we did test the ship loading, that is a rather busy moment in the port, where all the human drivers are going there as well, and the automation trying to keep safety distances to everybody might not work as well if in the mixed fleet. So mainly the case today was the rearrangement of the trailers to optimal positions. So we had some 25 hours of operations, and for sure the automated vehicle did move a little bit slower than the human, but that was not really an issue. The vehicle could drive, the automated vehicle could drive even faster, but it was in a sense funny that the surface at the port area was rather bumpy. And if the area is very bumpy and the vehicle is shaking, the collision avoidance features of this vehicle start to consider if the ground has become suddenly an obstacle during the bump. Anyhow, the energy consumption in this case, as you heard from me discuss the previous case where it was worse, here we are seeing pretty much zero effect. The vehicle is braking 2.5 times more than a human driver, yes, but it's otherwise driving much more fluently. So I would say that if the difference in braking is like the two times more braking cases, mild braking cases, then the eco-driving is about the same as humans, and if we can further reduce the number of braking, then we might do better in eco-driving perspective than humans. Due to some speed difference here, we still see the overtaking, and that is an issue if we are trying to operate during the very peak hours. Therefore, we see the most plausible case here is to operate during off-peak hours to rearrange the trailers, and that is the thing that is being studied in the future. The main hurdle, I would say, is connecting and disconnecting trailers automated. Even for a human, the connection process takes 2 minutes, and that is rather long, and we see, like here at the expo, we see some experiments on automating the trailer connect and disconnect. But to do it still automated in a mixed fleet, that is a challenge, and would it require a robotic arm, or we shall see what it will require. There was one case, one very busy intersection as well, which the safety driver felt that they always have to handle manually. And it was interesting that they saw the need to wave their hand that now it's your turn to go. And an automation cannot simply do this. We may see that it might be possible for a teleoperator to handle this intersection, but it would always need a teleoperator. So rather I would think that there is sometimes a need to consider the infrastructure. Do some changes, remove that intersection, drive a little bit different route. These start to be my final slides, but port simulation. So at the port, if every trailer is perfectly aligned, we save 15 minutes of ship loading time, and that's 2,500 euros. And if let's say 5 humans do the work of rearrangement, and some of the money is spent on their work, there are savings of, say, 700 euros. If we have 5 automated vehicles to do it, the savings vary depending on how much human support is needed. So the savings are from 500 to 800 euros. So if the automated connection of trailers is possible, automation becomes cheaper. If that is not possible and we all the time need the human to connect the trailers, automation is not cheaper than human in that case. So there is clearly potential here as conclusion. All our sites and demos show the economical potential. Let's say the price could be cut down to half or more. But now that this project has demonstrated that the driving part is rather possible, I would say, the next step to take is to integrate this driving to the industrial processes. And that may be a challenge in some cases. like with connection and disconnection of trailers. But if you have a fixed fleet, like at an airport, it would be rather possible to design and install, let's say, different connectors to these trailers. And at the other test sites, there might be things like at the airport, we would have to consider coordinating the whole vehicle fleet so that the automation knows where it is supposed to park. And that's not left to random human creativity where the vehicles are working. I see as conclusion, while Olaf said that he doesn't like teleoperator and so nobody really targets that. But I see that currently these vehicles would really need teleoperation support of some minutes per hour. Not automation by itself, but it's due to the interaction with humans. Humans are leaving luggage carts on the way, they are overtaking, they are doing something. And if automation would operate totally separate, maybe we would need no teleoperation support. But if we are pushing for this mixed operations, in this first phase of automation, I see we still need certain teleoperation support, and that is a research topic while as well a regulation topic. Okay, these were my slides today. Thank you.
Thank you very much for these presentations. So I am Victoire from the International Road Transport Union. So after having had a look at the operation and the vehicle, the results of the test, I will have a look at our experience with regulatory framework. So firstly, how is automation regulated? So it is regulated at different levels, and each level has a different focus. For instance, United Nations regulation sets and verifies technical standards for vehicles, including automation, specifically software updates, cybersecurity, and automated lane keeping assistance. Then when we go at the European level, there's a regulation for the type approval of the vehicles, which are the requirements that all vehicles must meet to be able to operate across the European Union. And lastly but not least, there is the national level that is the one validating the testing and the deployment of automated vehicles, as well as traffic rules and other rules, for instance, such as criminal liability. So obviously there is at the European Union level, there is a regulation of the type approval of vehicles, but then its application at national level is a bit different. You can see in the slides, it's kind of overview. And some countries have developed a framework for the testing of fully automated vehicles on public roads. When we say public roads, on certain predefined areas, not on all public roads. And this is the case in France and Germany. Other countries, such as Italy and Spain, do not have such framework. So what we have done in Award is kind of having also a look at this regulation, particularly for testing. We can have focused on a couple of countries, more in the deliverables, but ultimately we can see in the testing regulation and frameworks that there are some commonalities. Commonalities on insurance requirements, on risk assessment, risk mitigation. However, one of the differences is the ability to test with a vehicle, a safety driver outside of the vehicle, able to monitor the vehicle and take over the control of the vehicle at all times. For instance, this is possible in France and Germany, but not in other countries. So obviously, removing the driver from the vehicle has legal implications. Firstly, one of the biggest obstacles for testing and employing automated vehicles was the Vienna Convention, ratified in 1960s and signed by over 60 countries. It sets the requirements that all vehicles must meet. And one of them is that there is a driver within the vehicle and he is in control of it at all times. This is obviously an obstacle because vehicle automation kind of delegates the task of the driving to the automated driving system. So an amendment was made on November 2021 that deemed the driver criteria to be met by the ADS, however, provided that there is the monitoring of the human able to take over the control of the vehicle at all times. So this kind of opened the door for testing of automated vehicles. But this opens a question of, who is liable then of the cargo, who is also in charge of checking the vehicles, who is also what is the new testing and knowledge requirements for the human operators. So this is also something that we try to look into award. One of the first elements is the human operator. Obviously, one of the most tangible and visible changes is the role of the human operators. The gradual shift, as mentioned before, will be gradual, and this is kind of an example that we can see. At first, the ADS is in charge of driving the vehicles, but operator must be present within the vehicle at all times to be able to take over the control of the vehicle manually in case of needed. The remote driving, the human operator can take over at any time, but he is not located or she in the vehicle. Then we have the remote intervention, in which the human can only take over if the ADS requires it. And lastly, it's more of a monitoring role. So what you can see is that most countries require a safety operator within the vehicle. So this is the reality of today. It is possible in some countries, but not all of them. And if the European regulation foresees remote intervention, it does not foresee direct remote driving. So as mentioned before, remote driving is something that needs to be focused on within research to then looking at the the capacities as well as the limitations. And also one thing that could be interesting is to clarify the different types of teleoperation and the different needs and the different requirements to be able to have more clarity, especially at also a regulatory level if we want to start regulating and looking into it. Then there's also the question of the working conditions. Currently, the European regulation is regulating drivers' work. It's each of their activities, which is driving, availability time, as well as other work, is regulated. In the first time, as a remote safety operator does similar activities, such as driving, it can kind of fall under that scope, but as the role takes more of a monitoring role, this framework would not necessarily be adapted. Also, something that needs to be taken into account is the working conditions. How many hours can the teleoperator work? Also, how many vehicles can one teleoperator look at a time to be able to be as safe as possible, as well as how many are needed to be able to monitor the fleet at all times. So all of these items kind of require to start looking into them a little bit more. However, there's one, for example, at European level that should be start to look at is setting some conditions for the teleworking to ensure that the deployment and the testing is as safe as possible. Then also, as the role and the requirements and the activities shift, then there is also new training and qualification requirements. In a word, we had a look at what is in vigor across member states for the testing and deployment of automated vehicles, and it is kind of a patchwork. However, we can see commonalities, and these are we divided it into 3 categories. Firstly is the knowledge of the vehicle itself. So for this, it is required currently to have a driver license for the automated vehicle that you are operating. That means cars, truck, minibuses, as well as knowledge of the AV specifications and capabilities. Then we look at more specifically the remote operation and more specifically the safety procedures when intervening and taking over the vehicle. And lastly is knowledge on the specific operations, and that means the specific routes. For example, is it in a private area? Is there interaction with mixed traffic? This is very important, as well as some specific maneuvers, for example, loading and unloading. What we can say is that the minimum set of training requirements would be useful to set at the European level. Then we enter into the sphere of liability. So obviously, as more actors will be involved in the driving of the vehicle, liability becomes less straightforward because we go from a scenario in which the driver was in charge of the vehicle from A to Z, from the moment he turns off on the vehicle to when he turns it off, even after in certain cases, to a situation in which it is the automated driving system that is driving the vehicle until it requires the assistance of a human operator. There, the human operators take over the control of the vehicle, and in between these two, there is a fleet management system that dispatches the driving. So you can see this is, in that sense, it is less straightforward. And for this, it is really important to clearly define the tasks and the handover responsibilities between drivers. And that means both the automated driving system and the human operator. Also, one important element that it is enabled by the fleet management system is to monitor the handover. This is extremely important to be able to identify who is driving at all times, and which is especially important to define liability, especially in case of accidents. As a note, it is important to note that liabilities regime are national competences. What does that mean? It means that each member state has a slightly different approach to it. But what it is important, regardless, is that liability is clearly communicated and monitored to be able between stakeholders in charge of AV operation. This is under normal circumstances because what I mean is that in real life, the condition for the deployment of the vehicles may vary. What does that mean? One day it may be sunny and one day it may be rainy. This is what awards focus on. And here we kind of differentiated into 2 scenarios. One is be able to, there's some weather conditions that are not ideal, but enable safe deployment of vehicles. What does that mean? For example, a light fog. In these cases, to ensure the safety of operation, there's some mitigation measures that can be taken. For example, lowering the speed, increase the safety areas to mitigate the risks. Then there's other situations in which the conditions do not enable the safe deployment of vehicles. This can be the case of extremely low temperatures, extremely heavy snow, and in that case, the automated driving system is deactivated and there is no AV operation. What is important in all of this is that the more information is available and the more information is gathered by for the fleet management system and the automated driving system, the more they will be accurately able to monitor the environment and therefore know if the conditions are safe or not. This is why on our side, on the regulatory framework side, we state that setting a minimum requirements of data to be collected by the fleet management system and the ADS is necessary to ensure the monitoring and checking that the conditions are safe to enable deployment and testing, obviously. So this is what we saw. We also look at the obtaining a permit, because this was something that was very important in award, because this was a process that had to be done for the pilots. And once again, we looked at the situation across European countries. And obviously there's some differences, but we can kind of try to see the commonalities, and these we kind of divided it in three main categories. One is the safety assessment and mitigation measures. One is information on the operator. This is the safety driver or teleoperator. In this case, it is the safety driver. And lastly is information on the routes and areas where the testing will take place. However, there are some differences across member states in terms of what documentation is needed, the steps, and the timings. Obviously, they are they go all to the same goal, which is ensuring safety, and the test is safe, but it is different across all member states. For example, we have a concrete example from the hub-to-hub use case, in which the documentation and process was based on Austrian process and regulation. And when we see the timings, well, we know that the application was done in November 2022, and the certification was made available in June 2023. On that, I think from what our experience, we would like more clarity on permitting process at national level. This is why, is to try to avoid European fragmentation in this regard. And one element that could be interesting is to establish mutual recognition of safety assessment by member states. That means that a safety assessment carried by France could be accepted as well by Germany, and as it would enable to also try test across different member states without having to do everything from the beginning. And obviously there is obtaining a permit, but then it is ensuring that automated vehicle testing is safe, so the monitoring of this. Currently, there is data that needs to be shared with the national authority. But one thing that is also important and will be very essential is regarding the infrastructure and the vehicle, the maintenance of it. And this is why we have included in our recommendations to clearly set and communicate the respective responsibilities between stakeholders of the maintenance to ensure the safe deployment of conditions. And this is maintenance of the automated driving system, maintenance of the vehicles, and maintenance of the infrastructure. So as you can see, we have touched upon a lot of various elements. Obviously, there will be more into the final document of award, but these were the most pressing, also linked to what we have seen before. And now I will give the floor to Diana to look at the business models.
Thank you, Victoire. Hi, I'm Diana Reynales from Cara, and I'm going to speak about the emerging business models. Well, first of all, I'm going to speak about the market analysis that we have done to have the context to estimate the emerging business models, and after that, I will show you the first conclusions about the new emerging business models that we have found, because we are working still on the estimation of the emerging business models. So, regarding the market analysis, we have defined the market segmentation, first of all, of autonomous vehicles and fleet management systems. First of all, autonomous vehicles can be classified regarding the level of autonomy, as Benica said before. And they can also be classified by vehicle type, geographical areas, and application. Regarding the level of autonomy, Benike has already spoken about that before, so I'm going to try to make it short. We have levels 0 to 2, which are human-driven vehicles, and levels 3 to 5, which are autonomous vehicles. Level 5 is the total autonomy. There is no human intervention, but we haven't reached it yet. Now the most developed technology is level 4, which is no human intervention, but in geofencing, in specific geographical areas. And level 3 is autonomous vehicle, in which we need still a human in case of emergency. Regarding the type of vehicle, we find the the same classification for conventional vehicles. It's a classification regarding the weight of the vehicle. The scope of our project, of the award project, are heavy vehicles, so classes 6 to 8, medium duty and heavy duty vehicles, lorries and trucks. By geographical areas, we have 3 main regions that are today the leaders of the market. These regions are Europe, North America, and China, and they are supposed to be the leaders during the next years too. We will see it later with more details. The main problem of Europe, as Victoire has already said, is that we haven't harmonized our regulations yet, and there are differences among the different countries. And finally, we can find the classification by application, which can depend it depends on the type of road, if it's indoor or outdoor applications, the weather conditions, the traffic jams, etc. And we, in the award project, we have focused in 4 use cases that have been already presented. So now I am going to speak about the market segmentation of the fleet management systems. Fleet management systems can be classified by region, by component, and by deployment. By region, we have the same 3 main regions than before: North America, Europe, and Asia. Today, Asia are the leaders, but North America is supposed to have the most important growth rate during the next years. So it might change. And by component, we find 2 main types: operational management and performance management. Finally, we can classify the fleet management system by deployment. We have on-premise and cloud-based systems. Today, the more common ones are on-premise systems, but it is supposed to change during the next years. And cloud-based fleet management systems will take the leadership. Now I would like to speak about the market drivers. Market drivers are the factors that might push the deployment of the new business models. And we have different types of market drivers. We have the political and legal drivers. In Europe, we have already developed some regulations and laws that encourage the deployment of autonomous vehicles because they are related to the environmental performance and the improvement of working conditions. Regarding the economic drivers, we have the full cost. The main driver will be the improvement of the performance, the global performance of the routes. Because if we can automate routes, we could reduce the use of fuel and the time of route. After these drives, we can find the social drivers, which are consumers' behavior. When I speak about that, we have to think about the environmental issues. The consumers today are really concerned about the environmental subjects and the growth of e-commerce, because e-commerce encourages to develop the autonomous vehicles, because we need more and more logistics, more and more transport. So it's a very important driver for the deployment of autonomous vehicles. Regarding the fourth driver, we have the technological drivers. 5, the deployment of 5G, the real traffic monitoring, etc., and the environmental drivers, which are linked with the social drivers too. We know all the environmental problematic today, and electrical vehicles could help could bring a solution. After the market segmentation of the market drivers, we can find the barriers and opportunities. Regarding the barriers that might stop or make slower the deployment of the new business models, we can find safety and cybersecurity as main barriers. Safety is supposed to become an opportunity when the technology will be more mature. But now it's a barrier because we have found that there are lots of still too many emergency stops. And when I speak about security, I mean hacker attacks. And regarding the opportunities, we find the safety again, because even if now it's a barrier, it might become an opportunity if we reduce human-related mistakes and human accidents. And efficiency, the global performance, is an opportunity too, because as I said, the autonomous vehicle might help improving the global performance of the logistics change, and it would reduce the cost. Regarding the market size, we have the total addressable market and the serviceable addressable market. The total addressable market is the global market, the global existing market, and the serviceable addressable market is the market that we are focusing on. The award project focuses on the European market, which is in the forefront of the autonomous vehicle adoption. Sorry. And the market size depends on the capacity of implementing testing, large-scale testing. And regarding the serviceable addressable market, it's the market that we are focusing on, as my colleagues have already explained. We have 4 main use cases in the award project, which are the have-to-have, the port, the airport, and the forklift operations. We have studied the size of each one of the use cases. So I am going to sum up each one I'm going to start with the port. We have 1,200 commercial seaports in Europe, being the Netherlands the leader of this ranking. That makes 3 billion tons of freight handled every year. And the ports all the ports in Europe have different types of automation. In fact, we have found that container terminals are more propitious for automation than passenger ports, because passenger ports are more chaotic. However, container terminals follow organized procedures, so it might be easier to implement the autonomous vehicles in these kind of use cases. Regarding the airport use case, there are 615 million passengers per year. Our market is the tractor for baggage handling. The most important airports of Europe are those from Paris, Amsterdam, and Frankfurt. And we have found that the most propitious airports to implement the autonomous vehicles are the largest one, because the total cost of ownership is smaller in the case of the largest airport. I mean, if we speak about small and medium-sized airports, we will need much more time to get benefits from the implementation of the autonomous vehicles. However, in the case of a large airport, the time is much shorter. Regarding the have-to-have, when I speak about have-to-have, I mean the first mile logistics, so the transport of freight from factories to logistic centers and vice versa. In Europe, we have 3 main corridors. The Blue Banana corridor has been the most important one during all the history of Europe. The Blue Banana corridor goes from the UK to northern Italy, crossing Germany and Austria. But thanks to the European Union and the economical deployment of the different countries of the European Union, we have 2 more potential corridors, which are the Irish corridor, which goes from Ireland to Belgium, and the Baltic corridor. This one is a potential one. It depends on the construction of the Trans-European network, which is a network of rail and roads, but it could be potentially a market. And finally, we can find the forklift operations. There are different types of forklift operations, indoor and outdoor. The award project has focused on the outdoor operations. Today, there are just 10% of the whole warehouses that are automized, but we have concluded that forklift operations are much more propitious to use the automated vehicles than airports or ports, because again we can find organized procedures. Ports and airports are much more chaotic, so it will be much more difficult to implement the automated vehicles. And now I would like to present you the first conclusion that we have estimated for the future emerging business models, the preliminary findings. First of all, we have defined the first added values that will be given by the automated vehicles. We have done some interviews to different industrial stakeholders, and they told us that for them the most important one are the reduced human personnel cost, the safety, the improved efficiency, as I said before. The global performance will be increased, improved by the autonomous vehicles because we will be able to automate routes too. The marketing because it gives an image of innovation, and the improved working conditions. And we asked them to which one would them purchase as a one-shot expense, and they answered that they will, for them, it will be a one-shot expense, the infrastructure and the safety validation. And finally, we asked them who should pay for the new expenses related to autonomous vehicles. And they responded that it will be the factory production sites and the vehicle manufacturers. And that's all by my side. That's the work that we have done until now regarding the emerging business models. I think we have finished our conference. I don't know if, Benica, do you want to add some final words? As project. Okay, so thank you.
Thank you, everyone. For you who are here in the room, does anyone have any questions for any of us? Yep, you might have to come up and say it nice and close so we can hear you. Oh, no, microphone, yep, here we go.
Thank you very much for the presentation. What are the objectives of the project for the coming year or years? You're talking about regulations or public roads. We've seen that the speed of the autonomous vehicle cannot go faster, but it can be a problem on public roads and stuff like this. What are you going to focus on the major changes these coming years?
Anyone want to take that one? The project's nearly at an end. Olaf?
I understood that your question was of what speed of the vehicle. Was that correct? Yes. So it's part of the regulation today that traffic actors should not be obstacles to each other, so that the flow should go smoothly. Because it's a risk also if one vehicle is an obstacle to another. But in the use cases that we are addressed here, speed is not the main issue, because in a port, for example, and in an airport, it's more important to have a flow 24/7. And of course, when a flight is departing, the luggage need to be at the plane. And that is also about when is the passengers coming. So it's about planning. What we see now, it's of course speed is related to other traffic actors. That is one topic. The other topic is related to is sensor technology and computer power, the power that is able to, and other traffic actors, that will be as it is. But the sensors and the technology is improving. And the third thing that is coming is V2X. But we have seen, we are now also in applied autonomies within the fleet management system and operation tool. We're also into mobility. So we're also driving in normal roads. And there we are now driving with in 40 kilometers an hour. And we'll increase the speed to 50 kilometers an hour the first quarter 2024. So that tells that the technology is improving. So I'm not so concerned about that.
Does that answer one part of your question? Okay. Do you want to focus on, maybe Victoire can comment a bit more on regulation?
Should I? Yeah.
Or just how far have we come with regulation? What have we learned, and maybe what's coming?
The European type approval is an important driver. Will you comment on that? Yeah. So there is a lot of concern, what I have seen from European industry, because we have now got a type approval for autonomous cars, vehicles up to 1,500, and the test institutes, they need to know how to test related to this type approval, because the standards that they are going to use when they do the type approval also have to be approved. So the standards have to be approved as well. And we must. I think it's very important that the industry and the institutes and the regulators push forward together, because we have a common goal. So any actor of these that try to delay or do not act forward will delay the whole process. And why it's so important with this process? It's safety, and we do not have enough drivers. And the third, China and the United States are going to take us on this topic. So we have to speed up, really. I'm a bit concerned about it, that we already are so much behind United States and China. And there are even also challenges on the production of batteries. So that is a challenge. So we have to speed up.
Yep, and we're all in it together. I think that's a very good point, Olav. Anyone else?
Salut. Donc, mon question c'est les technologies que vous avez utilisées pour collecter les données pour les véhicules autonomes.
I can do a spontaneous translation. It's about the technology that we've used for collecting the data. Keep going.
Yeah, I would say.
Or in English, yeah.
Yeah, in English. Which type of sensors do you use for autonomous vehicles?
I can answer that question. That's an easy mile question, and the answer is we use a whole bunch of them. I'm not going to tell you specific company names, but that's the objective. It's also to create a safety chain so that we're not relying on one particular brand or particular type of sensor. We use what we call a best-in-class network, and we're continually evolving the sensor set. So there's always more than one type of sensor on the vehicles, that each one is, or can also act as a redundancy for the other. Oh, we can't hear you. Is something going on with his mic? Oh, yeah.
So, I mean, you use different technologies to test the...
Yep. So EasyMile, we're a software company, but obviously there's a lot of different hardware that's involved in autonomous technology. So we're using various different hardware suppliers on the market to physically place onto the vehicles and integrate with our technology. Yep.
Okay. Another question is about the market. I've not understood some percentage about the markets are, some says that Asia has a lot of requests, but also Europe at second place. I've not understood that.
Maybe that's one for Diana. Do you want to comment on that?
Yeah, can you repeat the question, please? In which sense you don't understand that?
Yeah, about the market sharing of the autonomous vehicle, you showed that in some presentation you said that Asia shared 42%. In other percentage, I saw that Europe shared 34%. Can you clear this?
Oh yes. There are two rates, one for the fleet management systems and one for the autonomous vehicles. So yes, I should have said it clearer. In fact, there are two rates. One is for the autonomous vehicles and the other one for the fleet management systems.
The biggest one is for the fleet management or for?
Oh, I can't go back now.
Yeah, fleet management, the biggest one.
Okay. Are we good? Last chance with all these good people up on stage in front of you. Okay, yes, one more.
Hi, thanks for these very interesting presentations. I just had a question about the end users. How were you able to integrate their requirements in your systems and use cases?
Whoa, yeah, it's a complex answer, but a simple one at the same time. Olaf, you clearly got it. Go for it.
Yeah. As you saw, in the end users here are the users of the logistics. So my use case was typically that. So there, in this use case that I showed, is the factory. That is one group of the end users. That is the terminal operator that have that. So we in Applied Autonomy and the board, we involved them in workshops. And we showed some videos, so they understand that this vehicle is driving by itself. Then we are deep into the detailed things, how much packs or can these vehicles carry and so on. And the cool thing there is that we save them some money, because I showed a picture of a terminal tractor dragging a container lifting up. And their vision was about to automate the transport. And then they asked me, is this a good idea to use this equipment to lift the container up? And I said, is it easy to use? No, it's not, they said. Do you think it's easy then for an autonomous system to use it? Why do you ask? And then we went into the details, because then this wheels of this trailer is wider than the container, which means that it's wider also than the tractor. And then I asked them, this is the way we work. Then I asked them, how is it for you when you carry something on your back and it's wider than your body? You go into the doors. And the same will happen with the autonomous terminal tractor, will have something wider than themselves. So we are very much into the details and discuss things so they understand what they're working with. And that we went step by step, the value chain, whole way. Yeah.
That's the early stages of autonomous vehicles. There's not sort of a one-size-fits-all approach yet. Maybe we'll get there, but certainly with EasyMile, also from a commercial perspective, not just within this project, when we're deploying a vehicle or putting a new vehicle on a client site, it's almost a classic sales process. You've got the lead, but then it turns into a series of deep dive technical meetings and making sure it fits the client's needs. I imagine that in coming years that'll get a bit neater and a bit more sort of process orientated and a bit more standardized, but it's still early days for this technology. All right, dear audience, speak now or forever hold your peace. Okay. If there's no more questions, I think we'll officially wrap up. Thank you very much for being here with us. Feel free to come and chat to us in person if you need to. Thank you. Enjoy the rest of your afternoon, evening.